Okay, so now we have a question, 2017, question 49. A long hard train collides with a small fly. Assume the mass of the fly is negligible compared to the train. The train and the fly were initially moving to each other with the same magnitude of velocity. When they collide, they stick to each other, and they travel with the same velocity as each other. Right? So which of the following is true? So this is a qualitative question, so it tests more of a conceptual understanding. So yeah, so let's take a look at each of the options. Right? During the collision, the velocity of the fly changes direction instantaneously to that of the train. So that is true because the train initially is because this train has a much larger mass, right, than the mass of the fly. Right? The fly is so small. So initially they're moving towards each other. Um, Initially they're moving towards each other at the same speed v, right? At the same speed v. Then after that, right, because you can imagine that they stick together, then they move together, and the train is, because the mass is much bigger, it's basically unperturbed, right? It's moving at the same velocity v, right? So yes, it changes direction instantaneously to that of the train. So this is true, but in this question they're asking for the most true statement, so we need to compare in some sense relatively between all the options. Right, so next one, during the collision, the fly stops moving at some point in time since the velocity changes direction, right? So initially the velocity is in this direction. After that, for the fly, after that is moving here in this direction. So if you graph the velocity, it looks, if you graph the velocity, it's going to look with respect to time, right? So this time, so initially is this, then after the collision, okay, so it's going to happen so instantaneously that it looks very, very short, right? But if we zoom in the time axis, it's going to look something like that. Of course, maybe it's not linear, right? But it's just going to be something like that. So this is also true, but because at some point in time, no matter what this path is, right, it's going to cross the zero velocity, right? It's going to have some zero velocity at some point in time. So this is also true. Okay. Since the velocity of the fly must be zero at some time during the collision and is attached to the train also has zero velocity at that time. So uh that's not true, because the train always has, just because it's the time at which the fly, imagine that the fly is this squishy object, right? Imagine you zoom in to the time scale such that you can see the fly getting squashed, right? Then um at some point in time, right, what's happening in the middle over here is that the fly is actually getting squashed, right? The train the train is always moving at some velocity. It's crazy to imagine that the train has zero velocity at some point in time, right? Just because it hits a small fly, the train is always moving at v, but it will decrease by a little bit maybe, right? Just a very, very tiny little, but there's no way it can go to zero, right? And so even though the fly is attached to the train, right, what's actually happening here is that um the fly is attached to the train, right? And if the fly is attached to the train, the reason why the fly can have zero velocity while the train has some positive velocity all the time is because the fly is getting squished, right? The fly is getting squished. So in some sense, the 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 front of the fly, right? The front of the fly that is touching the train, that part, that front always is v to the right, right? It's always following the train. That part, right, is always following the train. But the back part over here, the back of the fly initially is going here at some velocity, and after is getting the fly will get squished, right? The fly gets squished, and and if you take the average, in some sense, the average of the average velocity of the fly weighted by its mass, right? Then at some point in time, the average velocity is zero, but the part that the fly is always attached to the train is always going to be moving at velocity v to the right. Okay, nothing, nothing. That it is the back of the fly that will go through this zero velocity, or is the average velocity of the fly will go through this zero velocity point, right? So this is false, right? The first two are kind of true, right? But the third one is definitely false. Now, after the collision, the fly must have gained momentum from the train. So this is not true because initially it's moving leftward. Initially the magnitude of the momentum is mv, right? The final magnitude of the momentum is also mv if the train is infinitely massive, right? If the train is if the under this approximation, right? Because it's only an approximation, technically speaking, the final velocity is slightly less than mv. So this is also false, right? There's so even if it's slightly less, there's no way that you have gained momentum because gaining momentum will imply that it's greater than mv, but that is not true. Okay, so initially it's equals, final is slightly less, right? But it's slightly less, but there's no way it could have gained momentum. Okay, part E. The train must exert a large force on the fly due to its large momentum. The force exerted on the fly is proportional to the momentum of the train. Um, this is this is not true because the momentum. This is not true because it is kind of false intuition, right? The the train has exerted a large force on the fly, right? Large is relative to what, right? Technically, the 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 total impulse that the train has imparted on the fly is only approximately 2 times mass times the velocity, the initial speed, right? It's only approximately this. So that's kind of wrong in the first place, right? And moreover, um, the force, right? Impulse changes momentum, right? How much force is actually exerted and how much impulse actually exerted is more a function of the question's geometry, how they collide, and how the collision happened, right? And it's not really so much related to the momentum of the initial objects, right? So this is appealing to your false intuition and is just generally wrong, right? Because the first part over here must have exerted a large force. That that appeals to your intuition that when you get hit by a train, it's a very large force. But actually, the force required to hit the change of momentum of the fly is quite small comparatively. Okay, so now all that's left to do is to compare A and B. And okay, so first of all, there's two. The answer is B. Okay, the answer is B. But I'm just gonna explain why A is less correct, right? In some sense, there's 2 points over here. One is that the fly changes direction instantaneously, right? Remember that nothing in physics is instantaneous. Everything always happens over some approximation of time scale, right? So if we zoom in the time scale into the nanosecond range, you'll see that the collision, the fly actually goes through this. It could be a very weird graph, right? It doesn't need to be this graph. It could be some other shape, but it's not instantaneous, right? There's always some time interval in which the collision happens, right? There's always some time interval in which it happens, and this time interval is, no matter how small, right? It's, if you zoom in enough, it's not instantaneous. So the first point over here is that the instantaneous part is wrong, right? The reason why I marked it as true just now is because if you compare the time scale of a human, right? Yeah, the time you take to blink, then yes, it is instantaneous, right? It's almost instantaneous. But if you compare the time that the electron orbits an atom or something like that, then of course it's not instantaneous. So this is more of a matter of time scale, right? So it is true in our it's kind of true, but it's not scientifically precise true. Okay. And the another one is the changes direction during the collision. The velocity changes direction. Okay, yeah. So it's actually this is the only inaccuracy uh there is, right? Because it's not instantaneously. Okay. So yeah, so B is correct because as mentioned here, there's always some curve that goes from minus V to V, right? Or slightly less than V. And and um and because of the intermediate value theorem, right, in math, basically it's just saying that a smooth graph, when you go from this point to that point, must intersect the zero, must intersect some in between somewhere, right? You cannot draw a graph going from this point to this point, from minus V to V, without lifting a pen, right? If you draw a graph going from minus v to v without lifting a pen, you'll always hit the zero at some point in time. Okay, so this is a more of a statement in analysis, math analysis. So the answer is B.